Okay, today we are going to present an example to explain how to apply the parallel axis theorem. On a previous video, we have been working with a homogeneous cylinder that, well, it is useful to exemplify how to find the components of an inertia tensor associated to some coordinate system fixed to the rigid body, in this case to the cylinder. And we started by taking a coordinate system right at the center of the cylinder. Okay, this is at the center of the homogeneous cylinder, and we introduced the coordinate system like this. Then, looking that it's a homogeneous cylinder, we can say that this coordinate system is associated with the center of mass of the cylinder. Okay, so the inertia tensor that we found, and I'm going to leave you the link to the video where we calculate this inertia tensor. Well, this inertia tensor is associated to the center of mass, and we name it as ICM. Okay, perfect. So if we remember the previous lesson to this one, we showed that the parallel axis theorem says that if we want to find a new inertia tensor associated to a new coordinate system, we can calculate it as m that multiplies the Kronecker delta jk r squared minus rj rk plus the inertia tensor of the center of mass jk. Remember that, well, this inertia tensor does not have to be necessarily the inertia tensor of the center of mass. It can just be the inertia tensor of a different coordinate system. The thing here is that if we know this inertia tensor and we know what is the vector r that points from the new coordinate system to the old coordinate system that is associated with this, well, we can find the new inertia tensor that corresponds to that new coordinate system. Let me show you on a figure. Let's say that we are going to put the coordinate system here, and we are interested in finding the new inertia tensor that corresponds to this coordinate system. Okay, and we know that from this coordinate system we can find a vector r that points from the new coordinate system to the old one. This is r. Okay, perfect. So that means that if we know the inertia tensor of this and we know what is the vector r, well, following this formula we can find the inertia tensor associated to this new coordinate system. That is what the parallel axis theorem says. Okay, perfect. So, and yeah, looking that we are working on the center of the cylinder and it is homogeneous, this particular inertia tensor is going to be of the center of mass. But remember, that doesn't have to be necessary. Perfect. So, okay. But, well, looking that we have put this new coordinate system at the perimeter of the base of the cylinder, well, we can find the vector r very easily. The vector r is going to be for the x coordinate. Well, looking that this is at the center of the cylinder and this is at the perimeter of the base, well, this distance is going to be a, because that is the radius of the cylinder. I forgot to mention that this cylinder is of radius a and a height h, of course, and well, yeah, the total mass is m. Perfect. So that means that the coordinate, the x coordinate is a, then the y coordinate, looking that, well, these coordinate systems are parallel and we are locating this. Maybe this draw doesn't help too much, but actually if we measure that, well, this is the coordinate system and we measure y in this direction, we see that in the y coordinate these two coordinate systems are located at the same point. So that means that y is going to be equal to 0. And the z coordinate, well, we can see that this is located on a distance h divided by 2 from the base, okay, because it is at the half of the height of the cylinder. So we have here h divided by 2. Okay, perfect. So it is easy to see that r squared is going to be a squared plus h squared divided by 4. It is going to be necessary to replace here in this quantity. Perfect. So to be able to calculate this whole thing, let me define a new quantity that we are going to call it as j for the indices j and k. This is just going to be, well, this, which is the mass times the Kronecker delta jk r squared minus rj rk, like this. So that means that the new inertia tensor is going to be ijk equals j jk plus icm jk, like this. Okay, perfect. But remember that on the video that we made calculating the tensor of, well, that is associated with this cylinder, we found that that inertia tensor that is going to be of the center of mass, well, it is defined in matrix notation as m divided by 12, 3a squared plus h squared here, 0, 0, 0, the same thing here, 0, 0, 0, 6a squared. Okay, this is what we showed on a video where we wanted to introduce how to calculate the inertia tensor of a rigid body, and we used the cylinder example. So that means that we only need to calculate this quantity that we have here, the j tensor. So let's do it. J, we're going to start by the 1, 1 component, and this is going to be equal to the mass of the cylinder times the Kronecker delta 1, 1, that multiplies r squared, and minus, well, it will be r1, r1, but r1 is a, okay? This is the vector r1, r2, r3. Perfect. So that means that r11 is going to be equal to, well, a squared, like this. So we have that m times, this is going to be 1, and r squared, well, is a squared plus h squared divided by 4 minus a squared, like we mentioned, and this is going to be equal to m divided by 4 times h squared. Perfect. So this is j11. Let's see what happens with j22. Well, we are going to have the mass, Kronecker delta 22, but that is 1, then r squared, which is a squared plus h squared divided by 4, minus, well, the component, the second component of the vector r, which is 0 squared, it is 0. So we have 0 here, and this is going to be m times a squared plus h squared divided by 4. Okay, perfect. So what happens with the j33 component? Well, this is going to be m times a squared plus h squared divided by 4 minus, it will be here, well, r3 squared, but r3 is, of course, h divided by 2 squared, and this is equal to, well, we can cancel these two quantities to get that this is ma squared. Perfect. Okay, so we are going to calculate now the j12 component, and we will have the mass times the Kronecker delta 1, 2, which is going to be 0, of course, times r squared, minus, we are going to have here the first component of the vector r times the second component of the vector r, but remember that the second component is 0. So that means that we are going to get 0 here, 0 minus 0, of course, is 0. So, okay. And as you can easily notice, this is going to happen again with the J23 component, because we are going to get another Kronecker delta that will be 0, and the second component multiplying here again, so this is going to be equal to 0. And remember, these tensors that we are dealing with, they are all symmetric, so that means that J12 is equal to J21, and well, J23 is equal to J32. Perfect, so there is only one component left, so we need to calculate J13, and this is going to be equal to the mass, the Kronecker delta 13 r squared, minus the first component, which is A, times the third component. It will be h divided by 2. Of course, this is 0, and we are going to get minus the mass times A times h divided by 2. Okay, perfect. So what we need to do now is to put every component on a matrix that is going to give us that the matrix JK can be represented as, well, the first component was mh squared divided by 4. So mh squared divided by 4 here. Remember that the components that involve the number 2, the second row or the second column, are 0. So this is 0, this is 0. And the J22 component was ma squared plus h squared divided by 4. So here we have ma squared plus h squared divided by 4. And the 3 component was ma squared. Okay. Then I remember that here we are working on the second column, so this is 0. And here on the second row, it is also 0. And for this one, we need to take the component that corresponds to the row number 3 and the column number 1, which is this element over here. So this is minus mh divided by 2 and minus mh divided by 2. Perfect. So, okay. Let me rewrite this matrix on a better way. We are going to take a common factor m divided by 4, and this is going to multiply h squared, 0 minus 2ah, 0, 4a squared plus h squared, 0 minus 2ah, 0, 4a squared. And again, like I mentioned, the new inertia tensor that is associated to this coordinate system that is at the base of the cylinder, well, it is going to be, well, the sum of the matrices that we already know. So it will be this matrix that is for the J tensor, and then plus it will be, yeah, this one, this matrix that we found on that video that I mentioned, the one where we calculate the inertia tensor of a rigid body using the cylinder example. So we get this sum of matrices, and well, if we make this sum of matrices to simplify, we are going to get that this can be seen as m divided by 12, 3a squared plus 4h squared, 0 minus 6ah, 0, 15a squared plus 4h squared, 0 here, minus 6ah, 0, 18a squared. Okay, perfect. So, as we have been mentioning, remember that the inertia tensor of a rigid body depends on where you locate the coordinate system. So, it is very easy to suspect that if we move the coordinate system, then we will have a different inertia tensor components. And that is actually what is happening right now. We move the coordinate system from this position to this position, and now the inertia tensor is different. And this difference, well, we can find it using the parallel axis theorem, as we have already done in this example. So again, this will be the matrix of the inertia tensor associated to the new coordinate system that we have put in the base of the cylinder. Okay, perfect. So this will be a very good moment to finish the lesson. This is the final result.